So we're looking at the calculus of motion. So we've got a particle moving back and forth linearly on a number line or up and down a number line, but it's linearly. So as the particle moves back and forth, its position at any time t is given by a position function, s at time t. And the rate of change in its position is going to be its derivative, and the derivative is the velocity. And then the rate of change in the velocity is the acceleration. I want to spell acceleration with 2 L's, but I don't think it is. If the velocity is positive, means that the object is advancing or moving to the right. And then negative means it's moving to the left or retreating. When we look at the sign of the acceleration, it tells us whether the object is speeding up or slowing down. So positive acceleration, I don't mean v prime, I just mean velocity. Velocity is positive or negative means the object is advancing or retreating. Acceleration, positive or negative. Acceleration positive means it is accelerating. Acceleration negative means it's decelerating. If we're ever interested in the speed of the object is always just a positive number. The speed is the absolute value of the velocity. Velocity is a signed entity. Speed is a positive number. Okay, so that's not getting everything there. I gotta zoom out. Zoom out. Zoom out. I'll just write smaller. That's in the crazy box. Okay, much better. Okay, so we were going to go through this other example that I have on here somewhere. There it is. I've got a function. S of t is t to the 4th minus 4t cubed. And we want to analyze the motion of an object that has that position. T to the 4th minus 4t cubed. I guess I need to give you a time interval. I do need to give you some sort of time interval. We have it in seconds. And I think in the last example, t was between 0 and 10. So let's use that same time interval. So what we did in the first example was that we looked at when the object was advancing or retreating, by looking at the sign of the first derivative. Okay, so in part A, give intervals on which the object is advancing or on which it is retreating. So remember, we found where it was stopped first. And then once we find where the object is stopped, then we could look at the sign of the derivative and answer the question. So the derivative is pretty easy. The derivative is 4t cubed minus 12t squared. We find first where the object is stopped by setting that equal to 0 and solve for t. Looks like we can factor out a 4 and the t squared. And then I'm going to have a t minus 3. So there are two places where it stopped, at the beginning of the interval at t is 0. And then the second factor is equal to 0 when t is equal to 3. So we're going to break our time interval from 0 to 10 into two intervals, from 0 to 3 and from 3 to 10. And we're going to look at the sign of the velocity. So I'm going to plug numbers into here. And we know that the velocity is 0, both at 0 and at 3. So I'm going to indicate that here. The velocity is 0 here. Velocity is 0 there. Now we're going to pick a number from each of these two intervals. We're going to plug it into here and decide if this factor is positive or negative. But we can kind of cheat because 4t squared is going to be positive no matter what t I pick. So just grab a number and plug it in here. So when t is 1, 1 minus 3 is negative. So my velocity is negative in there. And maybe when t is 5, 5 minus 3 is positive. So velocity is positive there. So it's retreating here. And it's advancing here. So let's write that as intervals. Then it advances on make it an open interval because it's not doing anything at time 3. And it's still going to be positive at time 10. So let's make that a closed interval. And that it retreats on the interval from 0 to 3. Open on both ends because it's doing neither of two things at 0 or at 3. What was the other stuff that we did with this function? Let me see. Imagine we want to know where this thing's accelerating and not. Part B, we want to know the speed of the particle at time 2 and at time 5. So part B, give the speed at time t is equal to 2 and t is equal to 5. So we're still using the velocity function, but we're using it in absolute value. So the absolute value when t is 2 is going to be, where is it? 4 times 2 squared times 2 minus 3 So that looks like 16. And let's call velocity units, units per second. Pretty fast little particle there. Then we plug in 5 for t. Oh, phone, go away. Let's see. See if I can see this. All right. And so let's go about right here. That pen isn't feeling so good anymore. Speed at time 5, that's not a good pen either. Is the absolute value of 4 times 5 squared times 5 minus 3. So 25 times 4 is 100, times 2 is 200 units per second. So far, so good? Okay, the next thing we want to know, find my handout again. In part C, determine intervals on which the particle is accelerating. Okay, determine intervals on which the particle is accelerating. So let me see if I can get that over there to that side of the board. So what I'd like you to do is take the second derivative of the position function. Why has that got a big old blank there? Zoom it. Too much. Just has a big old glare right there. It says determine intervals in which the particle is accelerating. And so what we're going to try to do is take another derivative and see whether that second derivative is positive or negative. So I'm going to go back before I factored it. I'm going to take a derivative from here. So that S double prime is 12t squared minus 24t. And so it'll be accelerating when that's a positive number, decelerating when it's negative. So we'll find where it's 0 and do the stuff at the number line again. I can factor out a 12t, and I'll get t minus 2 as the other factor. So there are two places where there is no acceleration at t is 0 and at t is 2. Cut our time interval up. There's no acceleration here, and we want the sign of this function. So again, I'll put it in the factored form so it's easier for me. We can pick a number representative of each interval, plug it in there. So when t is 1, the first factor will give me a 12, the second factor gives me -1, and then a positive times a negative is going to be negative. So it's decelerating here. If I pick 3, 12 times 3 is positive, 3 minus 2 is positive. So there's where it's accelerating. It accelerates on the open interval 2 to the closed interval 10. And now we're going to determine the total distance traveled on the interval from time 0 to time 10. So I'm going to erase that stuff in the middle and write back here in the middle. Find the total distance traveled on the time interval from 0 to 10. So we're going to find where it is at the 2 endpoints and at the places where it turned around. And it only turned around at t is equal to 3. So we're going to find the position at time 0, time 3, and time 10, and then see if we can make some sense out of it. So S of 0, put zeros everywhere, is going to be 0. It starts at the origin at time 0. The stopping time was at S is 3. So we have 3 to the 4th minus 4 times 3 cubed. 3 to the 4th is 81. 3 cubed is 27. 4 times 27 is 108. So it backed up and moved on the number line to negative 27. Now S of 10 is 10 to the 4th minus 4 times 10 cubed. So here's 10 to the 1st, 2nd, 3rd, 4th. 10 cubed is 1,000, so take away 4,000. So it's gone to the position of 6,000 on the number line. And so here's what it did. There's our number line. At time 0, it's here at the origin. Then it backed up to time 3, it's at negative 27. So it went 27 units to the left. But now it's going to turn around and go way the heck out here. At time 10, it's at 6,000. So here we said it went 27 units. Then it had to go back those 27 units and 6,000 more. So it traveled a total of 6,027 units to the right. So the total distance traveled is the sum of those two numbers. So I'll write it like this. It started out at S at 0, and then it came to a stop at S at 3. That's that 27 units. Then from that negative 27, it moved over to a positive 6,000 for a total of 6,027 units. Oops, I need a 0. And so if I add those two together, oh, it's 27, 27, 54. 6,054 total units traveled in that time. Okay? Pretty easy, huh? Okay. Now let's look at an object that is dropped or thrown. If you drop or throw something, it follows the path of a parabola, right? And the only thing acting on that, well, a couple things acting on that, how fast I let it go, the initial velocity, and then that gravity that pulls it back down to the ground. Okay, so if an object is dropped or thrown, it follows the path of the parabola with a known formula. It looks like the position at any time t is 1/2 the effective gravity times time squared plus the initial velocity times time plus the initial height. So now we're going to look at motion in the plane. If an object is dropped or thrown from a height called the initial height h0 with an initial velocity we'll call that one v0, then its height above the ground at any time t is given by the formula. It's called height at time t. Going to have a 1/2 effective gravity times time squared plus the initial velocity times time plus the initial height. Where if height is measured in feet, then the effect of gravity is going to be a -32. Negative because it's pulling the object back down to ground level. And so if I put a -32 here, that makes the coefficient of t squared a -16. If the height is in meters, then the effective gravity is a 9.8. When we're analyzing position, we have to do things like factor. I'm not going to be too keen on using 9.8. So let's keep everything in feet so that I can rig my expressions up easier to factor. And I don't have to mess with decimals. So here's that picture. We've got some sort of initial height here. Here's ground level. That object's going to take off and then eventually land. It takes off with an initial velocity. Like I said, velocity is usually written as a vector. And then its height above the ground at any time t is that h of t. It gives you that vertical distance. So my first example says a person is standing on a cliff, 112 feet high, throws a ball directly upward with an initial speed of 96 feet per second. So we're going to say that velocity is positive when it's going up and velocity is negative when it's going down. So when I say initial speed and the ball's flown upward, then my V0 is going to be that initial speed. So let me write these numbers down. Person. Standing on a cliff. See how high that cliff was again? 112 feet high. And throws a rock or a ball. Which one are we doing? A ball, 96 feet per second. So before I ask any questions, let's go to our general formula and replace H0 with 112 and replace the V0 with 96. So we're working with the height at any time t is a negative 16 t squared plus 96 t plus 112. That's going to answer all of our questions right there. And the first question says, find the height. Okay, we got that. Its velocity and its acceleration at time t. So this is the height at time t. Now you're going to give me the velocity at time t and the acceleration at time t. So call it out. What's the velocity look like? Plus 96. Right, that's the first derivative. The acceleration shows us that we are only looking at gravity acting on this ball. Okay, with no wind or anything like that, just gravity is acting on the ball. So there's the velocity and acceleration and the height at any time t. Now, when does the rock hit the ground and what is its impact velocity? So a wind means we're finding a t when it hits the ground. So here it is in our picture. This is when we want to find it. We want to know what time that it hits the ground. So what do you know about the height at the time that it hits the ground? Height is 0. Find time when height is 0. So let's take our height function, set it equal to 0, and see if we can solve for t. We have 0 is a negative 16 t squared plus 96 t plus 112. And I think I chose these three numbers because they're all divisible by 16, but let's see. Let's see if we can factor out a 16. Let's play it in negative 16 as well. Let's see, 16 into 96. I think that goes 6 times. And I'm pulling out a negative, so we're going to change the sign as well. So we'll make a negative 6 here. And that'd be a negative 6t. And notice that 96 plus 16 gives me the 112. So that means 16 goes into 112 7 times. Again, I pulled out a negative, so let's change the sign there. Now we're looking to factor that second degree polynomial. We're looking for factors of 7, opposite in sign, that add to -6. -7 and a +1, right? T plus 1, T minus 7. So set each factor equal to 0, you get T is equal to -1, T is equal to +7. But a negative time doesn't make any sense, so we throw that one away. That means it took 7 seconds to hit the ground. Hits the ground in 7 seconds. So now we want the impact velocity. So we have to take our velocity function and plug that 7 in for T. So we need -32 times 7 plus 96. So I'm going to multiply here. 2 times 7 gives me 14. 3 times 7 is 21 plus that 1 gives me a -224 plus 96. And let's see. 100 and how much? We'll go with that. It's negative because it's coming down. And then that's going to be in feet per second. So far, so good? Okay, let me see what the next question might be. How far does the rock travel in its flight? How far does the rock travel in its flight? So we have to figure out how far it goes up and how far it goes down. How far does the rock travel in its flight? So to answer the question, I want to know where its maximum height is. So then it goes up to hit that maximum height, and then it comes down to ground level. And I'm going to add those two weights together. How do you think we're going to find what the maximum height is? Where it changes direction. What tells us where it changes direction? Say again? The position? Kinda. How did we just said the change in direction when we're looking at rectilinear motion? Where the derivative is 0, where the velocity is 0. So that's what we want to do. We want to find the time at which the velocity is 0. And then we'll find the positions at each of those. So first, maximum height occurs when the velocity is 0. So again, we're looking for a t. We're going to take our velocity function, put 0 right here, and solve for t. So we're solving the equation 0 is equal to negative 32t plus 96. Move the 32t over and then divide by 32. It looks like it goes 3 times. Maximum height occurs in 3 seconds. Let's go ahead and find that maximum height by plugging 3 in for t in our height function. H of 3 is negative 16 times 3 squared plus 96 times 3 plus 112. So let's see, 9 times 16 is a negative 144. 96 times 3 is 288. And then add 112. So 288 minus 144 is a positive 144. 144 plus 12 is 156. So its maximum height is 156 feet. So here's what it did. It started out at a height of 112 feet. So the rock didn't travel that distance, but it went from there to a height of 156 feet. So it climbed from there to there, a height of, what's 156 minus 12? 44 feet? It climbed 44 feet to get to its maximum height. And then it has to come back down that 156 feet until it hits the ground right here. Right? So if you add those two distances, (44 plus 156), 200 total feet of elevation climbed and dropped by that rock, ball, whatever we're throwing. All I want to know out of this question. That was it. That was the end of that. You think you got it? Seen one of these examples, you've seen them all. Right, you probably did these kind of problems in pre-calculus without doing any calculus, where you had to find the maximum height by finding the vertex of the parabola. And we had a little formula to find the vertex of a parabola, but it's too hard to remember that. It's so much easier to take the derivative. That's really all I want to say about that section. We'll go back and learn how to take more complicated derivatives. We want to take derivatives now of composite functions. So let me show you some composite functions. We'll learn the chain rule. Suppose you have f of x is equal to x to the 10th. And another function, say u of x, is just some second degree polynomial, 5x squared plus 6x minus 4. Those are two elementary functions. We know how to take the derivative of each of them individually. The derivative of x to the 10th is 10x to the 9th. U prime will give me 10x plus 6. Pretty easy, huh? Now let's look at the composite of these functions. What does f of u of x look like? What does that composite function look like for this particular example?
5x squared plus 6x minus 4.
That's right. So now we have a compound function. It's a function inside of another function. And the chain rule tells us how to take the derivatives of stuff like that. Let's call this function y. Here's what the chain rule says. The chain rule says that if I want to take the derivative of y with respect to x, I first take the derivative of y with respect to u, and then I multiply that by the derivative of u with respect to x. So if you think of these as regular old fractions, it looks like the du dx would cancel, and you'd be left with a dy over dx. It's supposed to look like that. But this says, take the derivative of the function with respect to the outside rule, right? U is the stuff inside. So I'm thinking of this, f of u of x is u to the 10th power. It says take the derivative of this first. So in our example, the derivative of that first would be 10u to the 9th. So in our example, this thing is 10 times u to the 9th. Then it said go to the function u and take the derivative with respect to x. And the derivative of u with respect to x is just 10x plus 6. But you want your derivative in terms of x. So in the last step, substitute out the u and put the 5x squared plus 6x minus 4 in here. So I don't want you to look at it piece by piece like I did here. I want you to look at this as the derivative of this. So let me say that that's just y. And take a look at what we did first. Leave this alone, bring the power down, raise it to 1 power less. So you start with the outside rule. Use our power rule, bring the power down, raise it to 1 power less. Then multiply by the derivative of what's inside. Okay, so we're going to call that the general power rule. The derivative with respect to x of u to the n is n times u to the n minus 1 times u prime, where u is some arbitrary function of x. Take the derivative of the outside rule times the derivative of the inside rule. So let's try it. What is the derivative with respect to x of the square root of 10x plus 9? Well, as usual, we take the square root sign off and we put a power. What's the power? 1/2. So we write that as 10x plus 9 to the 1/2 power. And now we're going to take the derivative of that. So you ignore the 10x plus 9 for now. You start with the outside rule. Bring the power down, leave that alone, raise it to 1 power less. Outside. And now you multiply by the derivative of the stuff inside. So now you ignore the power, you're just working with the 10x plus 9. The derivative of that is just 10. That's what this says. Take the derivative of the power times the derivative of the stuff inside. And then you can simplify it. Half of 10 is 5. Then you can take that term with the negative power and put it on the bottom. Okay? We're going to have a chain rule for all of our derivatives. We want a sine of u, cosine of u, tangent of u, secant of u, cosecant of u, cotangent of u, e to the u, natural log of u. How you take the derivative of all of those is you take the derivative of the outside rule, right? The derivative of sine of something is a cosine of that same stuff, but then you have to take the derivative of what's inside. So we'll do all of this, I guess, on Wednesday, because we're out of time now. That went fast. Good to see you again. You got one of your homeworks? Anything you want to say? Everything's going okay? Here? Here? Okay, I took 1/2 times 10, because those don't have any powers on them. I can put them together. This has a negative power, so I put it on the bottom. But a 1/2 power on the bottom is a 1/2 power anytime is the same as a square root. Okay.